In this video, we're going to begin to look at ordinary differential equations. And this video is the beginning of a few videos that will look at an introductory level at differential equations. Now, differential equations can be used in a variety of situations where combinations of rates of change are involved, such things such as speed and acceleration. They all represent derivatives of the position, first and second derivatives of the position function. And combining these to solve problems such as net forces on objects and so on there's wide application for the use of ordinary differential equations, let alone partial differential equations. But this next series of videos will just be looking at ordinary differential equations. Now there are some terms we need to get used to. First off, we need to be clear about. So the order of a differential equation, I'm just going to use capital D dot here, meaning differential equation, and referring to ordinary differential equations. So the order of a differential equation is equal to the degree of the highest derivative. All right. Then the degree of a differential equation is equal to the highest power of the highest derivative. So let's have a look at an example here. We have y squared plus dy dx all squared is 1. Is a differential equation of order 1, okay, because the highest derivative is dy dx, first derivative. It's of degree 2 because the highest power of the highest derivative is the power 2, and the highest derivative is order 1, okay, so it has degree 2 because we have a square here. There are different forms of notation for differential equations, but they all mean the same thing. We can have y squared plus dy dx all squared is 1. Same thing can be written as y squared plus y dash or y prime, depending on how you want to say it. All squared is 1. Or we can have y squared plus y dot squared equals 1. This dot is most often used in relation to a derivative with respect to time. All right, so it's often used by engineers. Another notation, f of x squared plus f dash or f prime of x squared is equal to 1, or y of x squared plus y dash or y prime of x squared is equal to 1. Okay, 5 different ways of saying the same thing. Now, one of the things with differential equations we're looking for, in particular in this video, is how to find the solutions of differential equations. Okay, we will look at problems where we set them up, but the focus initially will be on finding solutions to different types of differential equations. So, okay, well, let's say we're given the solution y equals 2x plus their proposed solution, y equals 2x plus 3 plus a half times e to the power of 3x. And we want to know, is it a solution of this differential equation here, where d2y dx squared minus 3 times dy dx plus 2 times y is equal to 4x plus e to the 3x. So is this proposed solution in fact an actual solution? And the way to do that is to substitute, to find the various derivatives of this, first and second derivatives, because that's what the left-hand side here involves, then substitute them into the left-hand side here and see that the result, after algebra, agrees with the right-hand side. Then we know that this proposed solution is in fact an actual solution to this differential equation. All right, now let's have a look. So let's start. Let's find the first derivative, what dy dx. Well, derivative of 2x is 2, derivative of 3 is 0, derivative of a half times e to the 3x is 3 on 2 times e to the 3x. The second derivative, well, 2 disappears, and we're left with 3 times 3 on 2, which is 9 on 2 e to the 3x. Okay, well, let's substitute them into the left-hand side here. So the left-hand side gives us d2 dy dx squared is 9 on 2 e to the 3x minus 3 times dy dx, which is 2 plus 3 on 2 e to the 3x, plus 2 times the proposed solution from above. Expand out the parentheses, collect like terms. When we do that, we see that this and this cancel. A minus 6 cancels with a plus 6 here. We're left with just 4x plus e to the 3x, which is exactly what the right-hand side was for the original problem. So this proposed solution is in fact an actual solution for this second order differential equation. Second order because the highest derivative is 2, second derivative. Now, some more terms. A first order differential equation is linear if it can be written as y dash plus some function of x times y is equal to r some function of x. Okay. A second order differential equation is linear if it can be written as y double dash plus f of x times y dash plus g of x times y is equal to r of x. Okay, now these are linear in y, y dash and y double dash. In linear in y, first derivative and second derivative, because there's no powers of these, they're not multiplied together. Okay, they are just linear. They are separate operators in their own right, sitting there. Okay, they're not squared, they're not multiplied by each other, nothing. Okay, they sit individually. Notice also that, and something needs to be clear, f of x, r of x, and g of x can be constants. They can be 0, or they can be functions of x. Okay, so they can be constant, 0, or functions of x. Right, an example of a nonlinear differential equation is y double dash times y. Notice these are multiplied together, plus y dash is equal to 0. Nonlinear because if you look at the first term here, it's the second derivative times the value y. Okay, so not linear. Y double dash squared, same thing. It's to the power of 2 there. It's y double dash times y double dash. It's not sitting individually, uniquely by itself. Plus y dash is equal to r to the x, and so on. Okay, non-linear because of the square. All right. Is y equals sine x a solution to y squared plus y dash all squared equals 1? Well, let's check. Y dash is cos x. The highest derivative is the first derivative, so let's y dash is cos x. Let's substitute that in now. So y squared plus y dash squared is sine squared x plus cos squared x, which from the trig identity is 1. Therefore, it is a solution to this nonlinear first order differential equation. Okay, that's it.